Okay, so this is the notes for exercise 11E, geometric problems. So in this first example, we have OACB as a parallelogram. OACB, well, we already have the first letters written O and A, but we also need the C and the B. So it goes OACB. I mean, we have to follow the letters that are given there. It might seem a bit weird that we're not doing in alphabetical order, A and then not having a B there, but that's just unfortunately the way that this has been written, so we'll have to follow that. So we are told that O to A is A, so that there is A, and we're told that O to B is B, and that there therefore is B. Now X is the midpoint it's not the midpoint, that's a mistake. X is the point on AB such that A to X to X to B, that ratio is equivalent to the ratio of 3 to 1. Now, X is a point on AB. Well, AB isn't on the diagram. There, that diagonal is AB. Now, X is a point on there so that A to X to X to B is in the ratio of 3 to 1. So that means that A to X is bigger, and it'll probably be around there where X is. So that's going to be point X. This here, from A to X, is going to be 3 parts, and from X to B is going to be 1 part. So it's a ratio of 3 to 1. So question A, find the position vector of X. Well, the position vector is from the origin. So we need to know what we're trying to find out in question A is from the origin to X. So we want the vector O to X. Now to get from O to X, you can go 2 different ways. You could go along here and then up, or you can go along up there and then down that way. Either way will give you the same answer. So I'm just going to go along the top and down. That's the way I'm going to go. So I'm going to say O to X is equivalent from going O to A plus then A to X. So I'm going O to A and then A to X. Now O to A, we can see from our diagram it is just A. A to X, well, we don't know what A to X is. All we know is it's 3 parts of the whole line. So it's 3 parts of the whole line A to B. But 3 parts out of how many? Well, there are 4 parts altogether on that line, so it's 3/4 of the length AB. So A to X is equivalent to 3/4 of A to B. So we still have an A. We have 3/4 of whatever A to B is. Now A to B, well, I don't know what it is, but I can go this way. And so that'd be minus A plus B. So instead of A to B is minus A plus B. And then I can just expand this out if I would like. Just to tidy it up, we have an A, take away 3/4 of an A, plus 3/4 of a B, which ends up giving us 1 whole A, take away 3/4, so just 1/4 A plus 3/4 of B. And that is the position vector of O to X. Now part B asks us to show that X to M is parallel to O to C. So X to M, oh, where's M? Well, let's go back to the question. M is the midpoint of BC. So M is going to be there, the midpoint of BC. And I want to show that X to M, so from there to there, X to M there, is parallel to O to C. apparently these two lines, that one there and that one there, are parallel. I have to show that they are. Now, if you remember, the way to show that two things are parallel to show that they are a multiple of each other. So we're going to work out both x to m and o to c. So let's do o to c first. O to c. Well, I can go different ways. I'm just going to go along the top and then, sorry, up this diagonal and then along the top. So O to C is going to be, I'm just going to go O to A along the diagonal there, this one here, plus A to C. Now O to A is just A, and A to C, well this here, going that way, is the same as going along that direction, that parallelogram. They're parallel and the same length. So the top horizontal line going right is the same as a B. So O to C is just A plus B. So I've done that one. I now need to look at x to m. So x to m, well, I can go different routes. I could start here and go up, along, down, or I can start here and go down and up. It doesn't really matter. I'm just going to go down, along, diagonal, and up. So my x to m is going to be from x to b plus b to m. Now x to b, well, that's 1/4 of that whole line. It's a quarter of AB. And b to m, well, b to c, that is parallel to this one here, O to A. And because m's in the middle, and we know that this one here is A, that whole thing will be A, so just up to m will be a half A. So b to m is going to be plus a half A. Now, we want a quarter of A to B. A to B is just minus A plus B. So we have a quarter of minus A plus B. Plus a half A. So we then expand this out. We have negative a quarter A plus a quarter B plus a half A. Tidying all that up, you get negative a half A plus a quarter B by collecting the like terms. So we've now expressed O to C. Sorry, that's not quite right. I've made a mistake, haven't I? So that was wrong. Negative a quarter A plus a half A is a quarter A, positive a quarter A, and then we have a quarter B left over. So x to m is this, O to C is this. So we've worked out both of these, and we have to show they're parallel. So they are, one is a multiple of the other is how you show they're parallel. And to show that, what I will now write is just a little equation saying that OC is equivalent to XM. But I need to fix it because that's not strictly true. From our two results here, we know that OC, this one here, is actually bigger than this one here. So you need 4 lots of this one to make it the same as that. And so I need 4 lots of x to m to make it equal to OC. So therefore, we have the vector OC is 4 lots of the vector x to m. And I can then write that since they're parallel, since they're multiples of each other, they are therefore parallel. So that's that first example. Now, the second example. This one here. So it says triangle ABC. Well, in triangle ABC, A to B is 3i plus 2j, and A to C is I minus 5j. Find the exact size of angle BAC in degrees. So what I can draw here is just triangle ABC, A, B, C. A to B, well, we know this is 3i plus 2j. And A to C is I minus 5j. And we're asked to find the exact size of angle BAC, so that's that angle there, which I'm going to call theta. Now, in order to work that out, what I am going to use is probably the cosine rule. If I knew the lengths of all three sides, then I could work out the angle using the cosine rule. Now I can work this side out because it's just the vector of B to C. And to work out vector B to C, I can go up there and down there, and then that will describe what B to C actually is. So we're going to work out B to C. B to C is actually going from B to A, then from A to C. Now B to A, well, 3i plus 2j, I should have written it properly, is going along down that way, because we're told in the question going from A to B is that 3i minus 2j. Whoops. 3i minus 2j. Sorry, I missed the minus. And we're told that A to C is I minus 5j, and that's going from A to C. So the vector is travelling down along that diagonal. So to get from B to C, we're going to go up there, down there, which is BA plus AC. B to A is actually going the opposite way to the 3i minus 2j. So it has to be negative of that. It has to be negative 3i minus 2j. And then AC, well, that's just going following that line, following the arrow. So that's just going to be adding I minus 5j. So just expanding this out and tidying it up, you get a negative 3i, a plus 2j, a plus I, a minus 5j. You collect like terms, and we get negative 2i, take away 3j, is this vector here. Now, in order to work out this angle, I said I was going to use the cosine rule. The cosine rule doesn't use vectors, it uses lengths. So what I really need to do is know the length of each of these sides. And I can do that by doing the modulus of each of those vectors to work out the actual size of the vector. So I'm going to work out the modulus of that one. So, A to B. A to B. I want to work out the modulus. That's just basically going to be the square root of 3 squared plus a minus 2 squared, but minus 2 squared is the same as 2 squared, so I'm just going to write a 2 squared there, and that gives me square root of 13. I'm also going to do the modulus of A to C. And that's going to be the root of 1 squared plus a minus 5 squared, but that's the same as 5 squared, so I'm just going to do a 5 squared. And that gives me the root of 26. And then I'm going to do the modulus of B to C, which is the square root of 2 squared plus a 3 squared, because that's the same as doing negative 2 all squared and negative 3 all squared. And that gives me also root 13. So now I know that that length there is root 26. This length here is root 13, and this one, that length is also root 13. So now just apply the cosine rule. Now, as a reminder, the cosine rule is a squared equals b squared plus c squared minus 2bc cos of a. It's nice that everything seems to be labelled correctly. We've got our angle at point A, which is nice. So this length is little a, this length here is little c, and this length here will be little b. But what I'm going to do is just rearrange this, first of all, to get cos theta by itself. So I'm going to subtract those from both sides. So a squared minus b squared minus a c squared. And then I'm going to divide by negative 2bc. And that leaves me with a cos a. So cos a is that. But substituting our information in, that means that cos of theta is equal to the square root of, what was it? So a, root 13 minus, sorry, root 13 all squared minus b squared, which is root 26 all squared, and then minus c squared, which is another root 13 squared, all over minus 2 times b, which is root 26, times c, which is root 13. So you work all that out, you then inverse cos both sides, and then you end up with the fact that theta is 45 degrees. So you worked it out. Okay, this is part one video now, and later the next video will be talking about the next two examples.